All right, so how are we doing today? Good? Yeah? Working through that second test? Yeah, easy, right? Well, we're gearing up for the hardest test. So, yay, that'll be fun. Yeah. Okay, well, let's get started, and we're going to keep working in chapter 16. Okay, so you remember we were talking about substances that are amphiprotic? What's an amphiprotic substance? Okay, it can either be acid or base. Okay, and one of those amphiprotic substances was what? Water? That's right. So if water can be an acid sometimes, or it could be a base sometimes, then can it do the same thing with itself? I mean, two water molecules, couldn't one of them act like an acid and one act like a base? Yeah. It can, exactly. It sure can. So that's what happens, is that one water molecule as an acid donates a proton, and the other one acts as a base and accepts a proton, and this is our Bronsted-Lowry definition here. And we form the hydronium ion and the hydroxide ion. Now, of course, it's still neutral, right? The water's still neutral, because you have one hydronium ion and one hydroxide ion, so it's still neutral. And we do produce two ions. It's in dynamic equilibrium. So remember we said, oh, water is a poor conductor of electricity because it's all those molecules. So we're thinking, wait, now we have ions. What are we talking about? Is it still going to conduct electricity? Well, actually, no. Water is still a very poor conductor of electricity because there's really not enough ions to do that. There's only like, I don't know, a couple out of a billion that do this. So it's very, very small. Okay, so this is dynamic equilibrium, right? So we can write the equilibrium expression. So let's write that equilibrium expression. So we would say K is equal to what? What would it be? Okay, H3O plus raised to the power of 1, okay, times OH raised to the power of 1. Did we divide it by anything? Think. It's pure liquids, right? Yeah, perfect. So it's pure liquid, so we're not going to write H2 underneath there, are we? So this is it right here. This is going to be it. This is going to be our equilibrium expression. And we're going to call this K, we're going to say KW. And what do you think the W is going to stand for? Water, exactly. So this is the ion product constant for water. And it is a constant. Kw is a constant. Okay, and the constant it's going to be is 1.0 times 10 to the minus 14. Okay, that is the constant, the ion product constant for water. Now, this works for water, and it also works for acids or bases. So in water, we're neutral because these two concentrations equal each other. But if we're in an acid, then aren't we going to have more hydronium ions? Because it's acidic, right? Well, it's in dynamic equilibrium, so as we have more hydronium ions, we're going to have less hydroxide ions. Concentration is going to go down. So again, when we multiply them together, we still get the same constant. Same thing if it's in a basic solution, right? If we have more base, it's going to be the hydroxide. It's more basic. Okay, so the hydronium ion concentration is going to go down, right? And so again, when we multiply these together, we still get the same constant. So it works for an acid, base, or neutral solution. All right, well, let's see, what would the concentrations be for a neutral solution? Okay, so, so we would say set this equal to x, so this would be what? Equals x squared. If the hydroxide and hydronium ion concentration are the same, we'll call that x squared. So what does x come out to be? 1.0 times 10 to the minus 7, perfect, is equal to x. That is the neutral concentration. Okay, so that's the neutral concentration. Well, if we know this equation, and if I gave you a hydrogen ion concentration, could you find the hydroxide ion concentration? You guys could do that, right? Okay, so for example, if we had a hydrogen ion concentration of 1.5 times 10 to the minus 9th molar, could you plug that in your equation and get the hydroxide? Because you know this is a constant, isn't it? 1.0 times 10 to the minus 14 is Kw. All right, so let's find the hydroxide. So if we know that Kw is equal to the hydrogen ion concentration times the hydroxide, okay, we can use hydrogen ion, hydronium ion interchangeably, remember? Okay, so then we know that the hydroxide concentration is going to equal Kw divided by the hydrogen ion concentration. Okay, so that would be Kw is 1.0 times 10 to the minus 14. This is divided by 1.5 times 10 to the minus 9. So what does that come out to be? What's that come out to be? Who's got their calculator to divide that out? So what would it be? You can divide that on your calculator, 1.0. Watch your exponents, times 10 to the minus 14. 6.6 times 10 to the minus 6. Okay, so everybody got that okay? All right, so we can do that. So this is one of the equations that we're going to use. So let's just write this up here to remind us. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, because that's an equation that we'll use a lot. All right, that makes sense. But look at these numbers. Wow, 6.6 times 10 to the minus 6, 1.0 times 10 to the minus 7th. Okay, those are kind of hard numbers to work with, aren't they? All those exponents, minus 14, minus 9. So let's think of another way to represent the hydrogen ion concentration. And let's talk about using what we call pH. You guys know pH, right? We've heard about pH all the time. It's like the power of hydrogen. Okay, so what would pH be then? Well, pH is like the power of hydrogen, French. So we would say that P, lowercase p, capital letter H, equals minus log hydrogen ion concentration. And what do those brackets mean? Concentration in molarity. Perfect. So this is what pH is. So think of this as the P represents the minus log. The H is the hydrogen ion. Okay, so pH is minus log hydrogen ion. Okay, so this is log, not ln. So if we were to take the pH of neutral water, what would we say the concentration was? Minus log of the concentration, which would be what, 1.0 times 10 to the minus 7. Okay, so if we took that on our calculator, what do you think we're going to get?
7.
Yep, pH is 7. Yeah, that's neutral. So that's why neutral pH 7 all this time. We're like, why is it 7, not 5? Why is it 1? Because this is the auto-ionization of water. It's naturally occurring, and that's what the pH is. The pH is 7. Okay, that makes sense, right? Well, let's talk about sig figs and decimals. Usually we keep those separate. Sig figs and decimals are separate. Well, this time they kind of go together. We have significant figures in the concentration. So we have 2 sig figs, right? Okay, so 2 sig figs in this concentration translate to the number of decimals in the pH. So if I have 2 sig figs, then I better have what? 2 decimals, that's right. So maybe a way to remember that is a decimal is like a period. pH has a P in it, P for period. Maybe you can count the spaces for that, unless anybody's got a really good way to remember that. This is the number of decimal places or spots after the period in the pH. So if we're looking at the number of sig figs here is what? 2 sig figs, right? So then our pH has how many decimals? 2 decimals. Okay, so that's how it works. All right, so we could take the pH of any of that kind of thing, right? Are we good with that?
Yes.
Okay. Well, let's see. What if we said, let's put this equation up here because we're going to use this one a lot too. pH equals minus log hydrogen ion concentration. Okay, well what if I gave you a hydroxide ion concentration? So let's put that up here. Hydroxide ion concentration. Hydroxide is equal to 1.3 times 10 to the minus 2. Okay, there's your hydroxide ion concentration. And I want to know, what is the pH? Could you do it? No, this is the hydroxide ion concentration, right? So with the pH, I need the hydrogen ion concentration, not hydroxide. So I have to find the hydroxide first. I mean the hydrogen ion first, and then put it in here, right? So what's the pH? Did we? So how are you going to solve that? Kw is a constant, yes. So I'll put that up here. 1.0 times 10 to the minus 14. That's Kw. I want pH. There's your hydroxide ion concentration. What are you going to do? Correct. Okay, so what's the pH? I was like, close, close. All right, so did everybody get that? The pH was what? 12.11. How are you doing that?
Minus log.
Oh, no. All right, so what steps did you do? You have the hydroxide. We want pH, right? pH is defined as minus log hydrogen ion concentration. Do I have the hydrogen ion concentration? No, I have the hydroxide. So I can't use that in there, can I? I need the hydrogen ion concentration. To get the pH, I need the hydrogen ion concentration. Where's the hydrogen ion concentration? How am I going to get that? Kw is equal to the hydrogen ion times the hydroxide, remember? And this is 1.0 times 10 to the minus 14, isn't it? Yes, that's a constant. And don't I have the hydroxide ion concentration? Yes. So did you divide those out? Yes. And then you got the hydrogen ion concentration, which was 1 point, what? Yeah, times, wait, no, it was 7.7 times 10 to the minus 13. Exactly. Then you can put that in here for the pH. And when you get the pH, it's 12.11. All right, does that make sense? Is that clear? Do you see how you had to use both equations to do that? Okay, so that's the way we're going to work with pH. We're going to use both of these equations because sometimes you'll be given the hydrogen ion concentration, you can get the pH. Okay, that's easy. But what if you're given the hydroxide ion concentration and you still want the pH? Okay, can we work both of those? Okay, easy, right? All right, super. Well, let's do another one. Let's see if we can work backwards. Like, what if you're given the pH and we want to find, hey, well, what is the hydrogen ion concentration? So let's do that one. Let's say pH equals 8.37. And we want to find, well, what is the hydrogen ion concentration if that's the pH? So let's put our pH formula back up here. pH equals minus log of our hydrogen ion concentration. All right, now this is 8.37, so I'm going to put in 8.37 for the pH is equal to the minus log hydrogen ion concentration. I want hydrogen ion concentration all by itself, right, because that's what I want. So I'm going to move the minus sign over first. So that becomes a minus 8.37 is equal to, because you know if you multiply both sides of the equation by -1, that's how we did it. Okay, is equal to a log of the hydrogen ion concentration. Now I have to think of a way to get rid of the LOG. So how am I going to do that? 10x. That's right. So I'm going to take the 10x of both sides. So what happens is this would be 10 to the minus 8.37 is equal to the hydrogen ion concentration. Okay, you do want to multiply both sides by -1 first to get the minus sign over by the pH. So that's a minus 8.37. So then I take the 10x, so that's 10 to the minus 8.37 is the hydrogen ion concentration, and that comes out to be 4.3 times what? 10 minus 9. Okay, good. There you go. 4.3 times 10 to the minus 9 molar. Okay? Everybody can go backwards?
Yeah.
All right. Let's see if you can do it. pH of 4.8. What is the pH of 4.8? What is the hydrogen ion concentration for pH of 4.80? So pH is 4.80, 2 decimals. Give me the hydrogen ion concentration then. And what would that be? So you're going to do the same thing, right? You're going to take the anti-log and all of that, right? So pH is 4.8, so move the minus sign over, and then take the 10x of it. So what does it come out to be? 1.58 should really be 1.6 times 10 to the minus 5, exactly. Because this is what, 2 decimals, so I'm going to have 2 sig figs. So everybody got that? Okay. Oh man, this is so super easy, isn't it? That's so awesome. All right, here we go. We can do pH, and we know that the two concentrations in molarity multiplied together is Kw. Well, you know, those hydroxide ion concentrations are also the same kind of powers. So it's like, well, those can be kind of difficult sometimes too. So what we can now think about doing is saying POH. Let's put another equation up here. POH, what would that be? Is equal to, P kind of stands for the minus log. So if it's POH, it's minus log hydroxide. You got it. There you go. So that's the POH. Now POH is very different from pH. Okay, they're very different from each other. So here's a bunch of pHs and POHs. Ooh, so tell me how's the pH related to the POH on these?
14 minus inverse.
Oh yeah, so if one is high, the other's low? Yeah, so if pH is low, then POH is high, and then mathematically, yeah, that's right, because notice, is that true for every one of these? Yeah, so the pH plus the POH equals what? 14. Yeah, pH plus POH is 14, pH plus POH is 14, and so on, right? Okay, so that's another equation we can put up here. pH plus POH equals 14. All right. Does that make sense? Okay, so a minute ago we worked on what is the pH when the hydroxide ion concentration was 1.5, didn't we? Okay, so we can do that again. We could do that again. This time, or it was 1.3, right? 1.3 times 10 to the minus 2. We can do that again, but you can use a different set of equations to do that. So given the hydroxide ion concentration, we figured out what the hydrogen ion concentration was, and then we took the pH. Well, what if we do it a different way? Well, yeah. That's right. What if we took that hydroxide ion concentration and instead took the POH? And then subtracted the POH from 14. Wouldn't that give us the very same thing? It would give us the very same thing, wouldn't it? So you could use any of these equations in any combination of way that you need, can't you? Okay, so which way do you guys like? Do you like taking the using the KW, or do you just like subtracting it from 14 with the POH? Subtracting from 14? Everybody likes that way? Okay, so we'll do the calculations that way. We'll take the POH and subtract it from 14. as we work through all these problems. Is that way you guys like that one? Yeah, I think it's probably the easiest, isn't it? Okay, but you see the difference between pH and POH? And they both add together to be 14? Okay, awesome. All right, well, let's see if we can do another one. This time, we're given the pH. Let's do another one. We're given the pH to be 11.40. So pH is 11.40. And instead of asking for the hydrogen ion, this time I want the hydroxide ion concentration. All right, so you have your 4 equations. You can use any of them in whatever combination you need to find the hydroxide ion concentration. That's what I want. So you can work this way, you can work that way. All right, so see if you can get that one. Yeah, it's pretty close to neutral. 6, 7, it's 10 times more acidic, that's true, but. So yeah, acid rain is going to be a lot more acidic. All right. Okay, so if this was, your pH is 11.4, did you guys subtract it from 14? Yeah, and then you took the anti-log to get the hydroxide ion concentration. Is that how you guys did it? Yeah? So what's it going to be? 2.5 times 10 to the minus 3, and it's in molarity, right? Because isn't that what those brackets mean, is molarity? Okay, whew, that's easy, right? So what we're doing is working with these 4 equations. So we need to be fluid with these 4 equations. So can everybody work back and forth on these 4? Okay, do we have any questions about that? Everybody do that okay? All right, so that's what we're doing, is we're using those 4 equations and we're working through, given pH, can you find the hydrogen ion concentration, can you find the hydroxide ion concentration, those kinds of things. All right, good, awesome. Well, as we talk about pH, how do we measure pH? Well, you guys have done litmus paper before, right? Okay, so there's litmus paper. We can use indicators. Remember our phenolphthalein, and it turns pink, and acid-base titration? So you used indicators before. Well, this is a great indicator that you can make at home. You take red cabbage, and you chop it up, and you put it, barely cover it with some water, and bring it to a boil, and then turn it off and let it sit, and then strain it, and you'll get this liquid. Okay, this liquid is an indicator. So you can put stuff and test things around your house, right? Acid to base, and those are all the colors it turns. So you can go home and make your own indicator. Yay! And then you can test stuff, see if it's acidic or not. Okay, another way to take the pH is with a pH meter. And we're going to use a pH meter in lab, and it's going to actually measure the pH for us instead of using an indicator or pH paper. So it'll give us a digital readout. So we can do that as well. So that's the ways that we can measure pH. And when we're talking about indicators, there we have different indicators. Remember, the end point is where we see the change in color. And we want the end point to be close to the equivalence point, right? So we have different indicators for different pH ranges. Now, when we're talking about a pH change of 1 or 2 or like 3, what does it mean when the pH changes by a whole number, like a pH of 4 versus a pH of 5? It's a power of 10, that's right. So it means it's 10 times more. So if we go from 5 to 4, we're now 10 times more acidic. So 10 times more acidic. So that's why when we're talking about decimals with our pH, 4.8, that's going to matter, because if we're going 10 times more acidic for a whole number, then decimals can make a difference in the acidity and the pH. All right? Okay, well, now that we can use these equations in finding pH and POH and all that, what we want to do now is we want to start to actually calculate the pH of different acids and bases. Now we're starting to move in to taking the pH of acids and bases. Now we're going to start with the strong acids and strong bases. So what do you know strong acids and strong bases do? Strong acids and strong base. Yeah, completely separate, right? Completely. Is there dynamic equilibrium with a strong acid or a strong base? No, there's not. So if you know it separates completely and you know what the concentration of the acid is, can't you figure out what the concentration of the hydrogen ion will be? Yeah, if you know it all completely separated. Yeah, so that's what you're going to do. And this is the beginning of what we're going to be working towards in Chapter 17, where we're working through these titrations. We're going to do some titrations in Chapter 17. It'll be the hardest exam. And we're going to have, what, 3 different titrations. Each titration has 4 different regions. Yeah, so this is a strong acid is going to be region 1. So we're going to, when we get to that titration and we hit region 1, I'm going to say, oh yeah, remember that one? That was we did that already. Okay, and when we take the pH of a strong base, and we'll do that as well, that's going to be region 4 of our strong acid base, strong base titration. Okay, so when we get to that point, we'll say, oh yeah, region 1, we already did that. Oh yeah, region 4, remember? We did that. Okay, so you're going to have to remember how to do these things, and we're going to pull it together in a titration problem. So we need to remember these pieces now as we build toward Chapter 17. So let's calculate the pH, HClO4. Is that a strong acid?
Yes.
Yes, it is. So what do I know is going to happen with a strong acid? Completely separate, right? Okay, so I want the pH of that. Well, the pH, let's look at the pH equation. pH equals minus log, what do those brackets mean? Concentration and molarity. Do I have molarity for that first problem? No, I don't.
What do we have?
I have what?
Liters and grams.
I have grams, yeah, and liters. Okay, grams to moles, everybody can do that. And then from, once I have the moles, what do I divide by? Liters, and that gives me molarities, right? Okay, so let's do that. Let's see, let's start with our 4.425 grams of our perchloric acid. So the moles, let's start with the 4.425 grams of our acid. And then we're going to convert that to moles. We all know how to do that with molar mass, so we'll have 100.5 grams of the acid on the bottom. Molar mass is equal to 1 mole of the acid. And that's going to give me 0.004229 moles of my acid. Okay. Now, once I have my acid, then I can divide by my 2 liters. So let's divide that by 42289 divided by the 2.0 liters, and that's going to give me the molarity of the acid. And the molarity of the acid is 0.002114 molar of the acid. Okay, that's the full acid. That's not the hydrogen ion concentration. That's just the molarity of the perchloric acid. I have to have the hydrogen ion concentration. Well, let's see. How am I going to do that? That's a mole-to-mole ratio, because perchloric acid, HClO4, does what again? Completely separates. Okay, so that'd be a hydrogen ion and a ClO4 minus, right? Okay, so this is a 1-to-1, isn't it? It's a 1-to-1. So it's going to be the same. So if this is the molarity of the perchloric acid, and it's one hydrogen ion to the whole structure of the acid, then it's 1-to-1, isn't it? So if it completely separates, so if this is what I'm starting with, 0.002114, and it completely separates, isn't this the same molarity for the hydrogen ion? Okay, so let's write that down. Okay, so hydrogen ion now equals 0.002114. So can I get the pH of that? Sure. pH equals a minus log of the 0.002114. And what does that come out to be? 2.675. Yep. That's my pH. Okay, so you see how we took the pH of a strong acid? You have to completely separate it. Watch the mole-to-mole ratio. All right. Questions about how we do that? Well, let's work on some bases now. Now, you guys remember your 7 strong acids, right? Yeah, yeah. Because it's important to know this part, if it's a strong acid or not, because how are you going to get the hydrogen ion concentration? Okay, you need to know it's a strong acid, that it completely dissociates, so you can get the hydrogen ion concentration, right? So you remember those. That's going to be crucial as we start to introduce weak acids. You have to really know the difference between the two, because they are solved different ways. Okay, so remember those 7 strong acids, right? Okay. Now, you guys remember the strong bases?
Yes.
Yeah, what were the strong bases from the periodic table?
1A.
Group 1A and
Strontium.
calcium, strontium, barium. Okay, those are the strong bases. So let's do one where we calculate the pH of a strong base. So sodium hydroxide, okay, sodium hydroxide, is that a strong base, sodium hydroxide? Yes, so what does that mean? Completely dissociates. Okay, so let's write it completely separated. And I see that the hydroxide ion mole ratio to the sodium hydroxide is 1 to 1, isn't it? So here we're given the molarity is 0.010 molar of the base, so guess what the hydroxide ion concentration is going to be? It's the same, exactly. All right, I still want pH. Uh-oh, this is OH. So what am I going to do to find the pH? You're going to take the POH? Is that what we like to do in the POH? Yeah. And then do what? Subtract it from 14? Yeah, exactly. Yep. So it is 12. So I take the POH. Okay, everybody knows to take the minus log of 0.010. That's the POH. And then once you get that number, you subtract it from 14, right? So pH comes out to be 12. Did everybody get 12? Okay. All right, because that was a 1 to 1. So I have the POH, so it's minus log 0.010. Okay. And then you subtract it from 14. All right, does anybody have any trouble with that? Are we good? Is everybody okay with that? All right, well, let's do the next one. Let's do the one with calcium hydroxide. Okay, so let's put calcium hydroxide up here. All right, so calcium hydroxide, let's write the equation. Is that a strong base?
Yeah.
Okay, so it completely separates, right? Okay, what does my equation look like? Calcium ion plus hydroxide. Make sure it's balanced. Is it balanced? What do I need? 2 and 2 in front of where? The OH. Okay, so my molarity is 0.010 molar. Same molarity. How about that? But how am I going to find the hydroxide in this case? You have to multiply it by 2. Does everybody see why? 1 to 2. So multiply that by 2. So what does that become? 0.020 molar. All right, so how do I find the pH of that one? What? Take the POH of that again, which is minus log hydroxide. So take the minus log of 0.020. And then subtract it from 14. So that answer comes out to be what? What's the pH for the calcium?
12.3.
Yep, 12.3. And for the sodium hydroxide, we said it was pH of 12.00, yeah? So look at the difference. The pH is different, isn't it? The pH is different, even though we start with the same concentration. So you have to be careful about how these completely separate. This is completely separated to 2 hydroxides. That completely separated to 1 hydroxide. But you know that strong acid, strong bases completely separate. So we should be able to get the concentration of either the hydroxide or the hydrogen ion, right? Okay, so the very last one. See if you can do that one. Let's see. So you found the hydroxide concentration, right? It was a 1 to 2, right? Okay, so that would be what, 0.250? Then what did you do with the 0.250 molar of the hydroxide? Took the pOH of that, so that's a minus log of that. Then what did you do? Subtracted from 14? So your final answer is 13.40? Oh, awesome. Okay, very good. Whew, awesome. You guys are doing great. Okay, how about you do that one backwards? Okay, this time you're given a pH of 12.05. That's pH. You got to pay attention. That's not pOH. That's pH. And let's work it backwards to get the calcium hydroxide concentration. So what'd you do with the pH? Subtracted it from 14? Did everybody do that? And that gives you the pOH. Okay, so what are you going to do with the pOH now? You're going to take the anti-log of that, take the minus anti-log of that. Did everybody do that? Okay, so you subtracted that from 14. And then you take the negative anti-log of that. Okay, so then that gives you the hydroxide ion concentration, didn't it? Okay, so let's put that hydroxide ion concentration up here. So the hydroxide ion concentration you found was what? Okay, so it was be 0.0112, something like that. That's the hydroxide ion concentration, isn't it? Now, what do we want? Do we want the hydroxide ion concentration or do we want the calcium hydroxide? Calcium hydroxide. So this is a 2 to 1, isn't it? That's right. So it's 5.6 times 10 minus 3. Yay! Perfect. All right, everybody got that one okay? All right. Well, let's look at the next one when we start mixing acids together. Ooh, that's a fun problem. Okay, so let's talk about how we would solve that problem. Now, you can mix acids together. So we're going to mix two strong acids together. And after we've mixed them together, we want to know what is the new pH. Now, you can also do this with strong bases. Mix strong bases together, and what's the new pH? We'll do this one with mixing the two acids together to see what is the new pH. Okay? So, what I have is let's erase this right here. I have a solution. Here's my beaker, and I'm going to pour in hydrochloric acid and hydrobromic acid. Are those both strong acids?
Yeah.
Yes, they are. So I'm going to pour in these acids. And I'm going to have a solution here. And the question is calculate the pH of that solution. I need the pH of this solution. So we know that pH equals minus log hydrogen ion concentration of this solution. Okay? Well, those brackets mean what? Molarity. So I need the molarity of the hydrogen ion of the solution. So that molarity is defined as moles of the hydrogen ion divided by, remember the definition, total liters. Okay, so what's my total liters in the beaker? Okay, so I had 10 mils. So let's write this here. This is going to be my HBr. HBr at 10 mils, and it's 0.1 molar. Okay, so I'm going to go ahead and change that 10 mils. Everybody okay to change that to liters? All right, so change that to liters. What is that? 0.01 liters. Okay, and then here's the other one, HCl, and this one is let's change that to liters, 0.020 liters, and it is 0.2 molar. So if I've got 0.01 liters and 0.02 liters, and I'm putting them together, then my total solution is that's right, total solution. So let's change that and put down 0.030 liters. There we go, I'm almost there. So I have the total volume. I just need the total moles. Okay, well, how many moles am I getting in here? That's the question. How do I figure that out? How many moles of the hydrogen ion? How would I get the moles of the hydrogen ion? Ooh, so molarity times liters is moles. So if I multiplied the molarity times the liters, that would be what? Moles of this one. Okay, that's one of them, but I'm also putting in some of this, the HCl, aren't I? So can I do the same thing, multiply the molarity in liters, and add the two together, couldn't I? Yeah, ta-da! So let's do that. Let's say molarity times liters, we know, is equal to moles. So if I have 0.010 liters times 0.100 molar, that equals 0.00100 moles of my HBr. But we know that's a strong acid, right? So hydrobromic acid separates into the hydrogen ion plus the bromide ion. So isn't that a 1-to-1? Okay, so I have the same 0.00100 moles of the hydrogen ion that I got from hydrobromic acid. Let's do the same thing for the other one, 0.020 liters times 0.2 molar is going to give me 0.0040 moles of hydrochloric acid. Well, this is a strong acid, doesn't it? It completely separates. So that's going to be completely separated. So let's write it completely separated. Hydrogen ions plus chloride ions. So isn't that a 1-to-1 So it's going to be the same, isn't it? 0.0040 moles of the hydrogen ion. Okay, so altogether, what do I have? I've got 0.001 moles and 0.004 moles going into the beaker. So altogether in the beaker, what do we have? We have 0.0050 moles of the hydrogen ion, don't I? Okay, so let's write that in. So the moles of the hydrogen ion is now 0.0050 moles. So the molarity comes out to be 0.1667. That's the molarity of the hydrogen ions. Okay, so I can put that in here and find the pH. And the pH is what? 0.778. That's the pH. Now, you're thinking, why can't we just add these together like we did before? We said, oh yeah, remember how we did the ice tables and we're adding the molarities and all that together? You can't do that here, even though we're used to doing it in the ice tables. Why can't we do it here? Because there's an important difference, and that is we have a volume change. And molarity depends on the total volume, doesn't it? So this molarity and this molarity are going to change. The molarities of the acids will change because my total volume changed. So if I have a total volume change, the molarity has changed. Because the hydrobromic acid is 0.1 molar, the hydrochloric is 0.2. We're like, hey, can't we just add that together and get 0.3 molar? No, because look at the molarity. It's not 0.1, it's not 0.2, it's 0.1667. And the reason is, why? Why is the molarity changing? Because there's a volume change. Does everybody see that? So once you get that, then you can get the pH. Whew. Okay, how are we doing? Okay? Good? Everybody good? All right, does everybody understand that one? Okay, awesome. So that's taking the pH, we said, of a strong acid and strong base, and now we're working with this. We understand about volume changes affect the molarity. Okay, well let's start. That was a strong acid. We did strong acids and strong bases. So let's do a weak acid or a weak base. We'll start with the weak acid. Now we said strong acids, do they undergo dynamic equilibrium? No. Well, what about a weak acid? Oh, yes it does. There's a big difference, isn't there? Weak acids undergo dynamic equilibrium. They are not strong electrolytes. So if you have HA, for anion, HA, weak acid, dynamic equilibrium, hydrogen ion plus the anion, A minus. So a weak acid will undergo dynamic equilibrium. It doesn't completely dissociate. Only some of it does. Some of it stays together, some of it dissociates. So we can write that like this, HA is to separate hydrogen ions and the anion, or we could write it with water, HA plus H2O. Again, dynamic equilibrium, that would give me H3O plus and A minus. So it's pretty much the same thing, right, isn't it? We said the hydronium ion is interchangeable with the hydrogen ion. Okay, so let's write our equilibrium expression, because isn't that dynamic equilibrium? Right, so we can write equilibrium expression. So let's write dynamic equilibrium expression. So we'll just do the first one here. So K is equal to, what would the first one be? These are going to be the same anyway. So it would be what? Okay, concentration of H plus times concentration A minus over HA. There you go. Okay, and it's all to the power of 1, right? The 1 coefficients. All right, so that's my equilibrium expression. And since it's the equilibrium expression of an acid, guess what I'm going to put right here? A for acid. Only for equilibrium concentrations of that acid. So it changes for every acid. Now, if it changes for every acid, how's that going to relate to acid strength? If Ka keeps getting larger and larger, Doesn't that mean I have more products than reactants? Okay, so more products means more hydrogen ions, right? And if it's more hydrogen ions, it's more acidic. Okay, so what are we saying then? The bigger the Ka, the stronger the acid. Exactly. The bigger the Ka, the stronger the acid. So the bigger the Ka here, the stronger the acid. Now you guys know the Bronsted-Lowry definition of an acid, right? Because we would need to write those equations. So what's the Bronsted-Lowry definition of an acid? What does an acid do? Bronsted-Lowry definition donates a proton. So you're going to have to write those reactions. So we would write it donating a proton. So here's several examples of acids, and we're going to donate a proton. Hydrofluoric acid, we're going to donate the proton. It is in dynamic equilibrium because we don't have a strong acid. These are weak acids. And you can put water in there or not. In these cases, we do have water. And here's benzoic acid. So notice that benzoic acid, we have a hydrogen in front and hydrogen's in the middle. Which is the one that leaves? The front. Do we ever lose one from the middle? No. Okay, so you guys remember that? We're going to lose, like acetic acid, you're going to lose the hydrogen in the front. So we can all write those equations, right? Yeah, so easy, right? Yeah, okay, so remember that. Okay, remember how to write that equation of losing a proton. Okay, so that's our Ka. And we can have dynamic equilibrium with our weak acid, so we can write an equilibrium expression, and we understand about Ka. So let's look at some Kas of polyprotic acids. Polyprotic acids is many hydrogen ions, so here we have lots of hydrogen ions here. Now remember when we were talking about acid strength? Which one is the easiest to come off, the first one or the second one? Everybody remember that? The first one's easier to lose, a little bit harder to lose the second one, a little bit harder to lose the third one. Okay, so our Kas reflect that. Okay, so the first one is going to be the bigger Ka because it's easier to come off, it's more acidic. And then the second hydrogen coming off, not so much. Third hydrogen is a little harder still, less acidic. Now, a lot of times we can just worry only about the first hydrogen coming off because that one is the most acidic. And particularly if there's a difference in the K values of 10 to the third or more, then pretty much the rest of the hydrogens are pretty negligible as far as contributing to acidity. And we just count on the first one. Okay, does that make sense? Now, there are some substances where you would have to take into account the other hydrogens coming off to contribute to the acidity because it's not as great. But if it's 10 to the third or more, then you don't have to worry about that. All right, does that make sense with polyprotic acids? All right, that's polyprotic acids. Okay, well, we talked about acid strength. Ka helps us understand acid strength. Well, there's another way to get acid strength, and that's percent ionization. All right, so how do we define percent? Percent is defined as what? Okay, does everybody remember that? Part, what? Over the whole times 100. So if I'm talking about an acid strength here, then that would mean I'm talking about the hydrogen ion, doesn't it? So percent ionization refers to percent ionization of the hydrogen ion. So the hydrogen ion is my part. Okay, so I'm going to put my part is going to be the concentration of the hydrogen ion. Now, do you remember it takes time for equilibrium to establish? Yes. So when I first start off, there's not much hydrogen ion. So I want to get to the point where I've got the maximum hydrogen ion that's going to separate. So in other words, the hydrogen ion concentration is steady. So at that point, I've had to have reached what? Dynamic equilibrium. So I want the hydrogen ion concentration at equilibrium. That's the one I want. The hydrogen ion concentration at equilibrium. And to do that, we're going to define pH. pH is going to be defined, pH is defined to be at equilibrium. Okay? So what is pH defined to be? At equilibrium. So if you're given a pH, then you know that that hydrogen ion concentration is going to be at equilibrium. Okay, so pH is to be defined at equilibrium. So pH is defined to be at equilibrium. So in other words, if I had pH, I could get that concentration, couldn't I, of the hydrogen ion at equilibrium? Okay, over the whole, guess what the whole is? Yeah, the whole acid. Now you want the whole thing before anybody starts to separate off. So you want the whole thing. So this is going to be the acid concentration at initial, before anything begins, times 100. And that's percent ionization. Okay, so see if you can calculate what is the percent ionization. You have a 2.5 molar solution. That's going to be the initial. And I need percent ionization. So see if you can calculate the percent ionization for that problem. Okay, so I have my acid initial, don't I? Yeah. So that's the 2.5, right? Okay, now I need the hydrogen ion concentration at equilibrium. Well, how am I going to get that? From the pH. Okay, so did we get that concentration from the pH? How are we doing on this one? Okay, so my initial concentration, that's the what? 2.5? Did you guys find the hydrogen ion concentration from the pH? Yeah. Yeah. Okay, let's put that up here. 0.0339, something like that. Times 100. All right, so what'd you guys get for percent? 1.36%. Okay, so we can find the percent ionization? Yeah, so easy. So easy today. So if Ka is bigger, what did we say about the acid strength? If Ka is getting bigger, what is happening to the acid strength? It's stronger. Okay, well, what about percent ionization, do you think? If percent ionization gets bigger, what does that mean? If the percent ionization is getting bigger, then it's becoming more acidic also. Exactly. All right, so if Ka is bigger, we're becoming more acidic. If percent ionization gets bigger, more acidic. All right, so that's two ways that we can talk about the strength of an acid then, isn't it? All right, and if both of them get larger, it means our acid is getting stronger. Okay, great. Well, we said, hey, a weak acid, that's dynamic equilibrium, isn't it? Sure, and we know all about ice tables. Yay, we're going to do ice tables again. This should be like a review. Oh, it's just a review. We've been doing ice tables over and over again. So, hey, this is an ice table again. It's like a review. Okay, we know how to do ice tables. Same thing. Now, we can get Ka. We can get Ka with our equilibrium concentrations, can't we? And don't we use the ice table to help us get those equilibrium concentrations? And then we plug it in and get the Ka. Oh, that's what we're going to do again. This time, since we're talking about acids and bases, we can do that with our acids. Weak acid is what we're talking about right now. So we can do that. We can find the Ka for a weak acid. So what we're trying to do is determine the pH. So here we go, or in this case, Ka. So here we have a situation, lactic acid. Okay, we have to recognize what that is. Well, it's an acid for sure. Is it a weak acid or a strong acid? Weak acid. So do weak acids undergo dynamic equilibrium? Yes. So does that mean I'm going to need an ice table to get those equilibrium concentrations? Yes, of course. So we know how to do that. So I have to have an equation. Oh, here comes that writing the equation of an acid. Oh, let's see. What was that Bronsted-Lowry definition of an acid again? Oh, it donates a proton. So can we write that equation?
Yeah.
Donating a proton? Yes, you need to write the equation for the ice table. And, oh, look at all those hydrogens. Which hydrogen is the one that's going to leave? The first one, exactly. Okay, so see if you can start working on that. We know how to do that, right? So first let's write this equation. I'll put this up here. Okay, so that's HC3H5O3 donating a proton plus C3H5O3 minus, right? And we're setting up the ice table, ICE. Okay, now you remember the first thing we have to do is write down all the information that's in the problem. So let's see what's in the information in the problem. Lactic acid is found in sour milk, which is produced by the action of lactobacilli on lactose and milk sugar, a 0.025 molar solution. Where does that go? 0.025 molar solution. That's the initial, isn't it? Under my lactic acid? Okay, so that's 0.025 molar. Okay, it's in molarity, so that's good. Has a pH. Whoa, what am I going to do with pH of 2.75? Oh, so you can get the concentration of the hydrogen ion, can't you? And where did we define pH to be at initial change or equilibrium? Oh, okay. So we define pH to be at equilibrium. So guess what? It goes on the E row. And we want the hydrogen ion concentration in molarity, don't we? Because this is tables in molarity. Yeah, but we know that because pH is 2.75. So can you guys all find the hydrogen ion concentration? We practiced that lots, didn't we? All right, so 2.75. Find the hydrogen ion concentration. I get 0.001778. Does everybody get that? Okay, so that's your setup. So what's the different thing? What's the one thing that we added? One little tiny thing on here. What was that? The part about the pH. Yep. That's the part that we added. And we know how to do pH. So this is the same exact ice table that we've been doing. We just added the part about, hey, how do you find the equilibrium concentration of the hydrogen ion? We get that from pH, because pH is to be defined at equilibrium. Okay, so there's your setup. All right, review. You guys know how to finish that ice table? Solve that ice table and see what you get for Ka. Okay, so we all know how to do an ice table, right? Let's just review now. This is just a review. We know how to do ice tables. We know how to do pH. We're just reviewing this together. That's all. Just putting them together. Let's see. 1 negative 4. Yeah, no, minus 4. Yeah. 1.36. Is everybody getting 1.36 times 10 to the minus 4? Yeah? Okay, 1.36 times 10 to the minus 4. Do we all got it? We got an ice table, right? We know how to do this. We should know how to do this. It was like test on this, right? Test on ice tables. Of course we know how to do it. This is not the time to learn. Yeah, test is going on. Okay, so is everybody okay? Easy. All right, how you guys doing? Okay? All right, so we put all these numbers in. Remember, you use your equilibrium concentrations in the Ka. So we put all those in, and we got 1.362, or 1.36 times 10 to the minus 4 is our Ka. Any questions? No? We got it? We feel comfortable with that? Okay, so we've done this, right? All right, well, let's see. Let's see if we can go again. This time it's a 0.1 molar acid solution, which has a pH of 2.25. Let's find the Ka and the percent ionization this time. So let's do it again. This time, let's find the percent ionization as well as Ka. Okay, same thing. Just practice again. This time, let's add in percent ionization, now that we've talked about percent ionization. All right, so we got Ka is 3.35 times 10 to the minus 4, or 3.47 times 10 to the minus 4, so that would be 3.3 times 10 to the minus 4 and 2 sig figs. Okay, so we have Ka, now what? How are you going to do percent ionization? So the equilibrium concentration, so that would be what? The 5.62 times 10 to the minus 3? So that is the concentration that goes here, right? It's the equilibrium concentration over the initial, which is 0.1 times 100. What'd you get for the percent? Everybody get 5.6%? Yeah, because we took this number because it has to be at equilibrium, doesn't it? Divided by the initial acid times 100, 5.6%. All right, questions about that one? Okay, boy, we're just zipping right along. You guys look so enthused. All right. Well, do you remember how we can do this one? Given the Ka, can we find the hydrogen ion concentration? And then guess what we're going to do? We're going to take that hydrogen ion concentration and we're going to get pH. All right, so given Ka, we're going to find pH. So let's do that one. All right, so here's the pH. We need the pH of a 0.250 molar, so let's write that up here for our initial concentration of our nitrous acid. So let's put that up here. All right. It's got my equation, which would be HNO2 separates into hydrogen ions and my nitrite ion. Now, initial is 0.250 molar. And that's all I have in my ice table, isn't it? It's just the initial. Okay, so we're going to have to fill in the rows. So we finished the first row. So these, the hydrogen ion 0 and the nitrite ion 0, right? Now what are you going to use for the change row? X. Okay, so this would be what? Minus X. This one's plus X. And this one's plus X. Okay, so this would be equilibrium is 2.50 minus X. Hydrogen ion is X. Nitrite ion is X. All right, let's put it into our equilibrium expression. Okay, so putting that into your equilibrium expression, what do we get? Oh, X times X divided by 0.250 minus X. Isn't that what we get? Okay, and we know the Ka is 4.5. Yep, 10 minus 4. Okay, so that would be 4.5 times 10 to the minus 4 equals X squared over 0.250 minus X. Okay, oh boy. Yep, that's a quadratic, isn't it? Yeah, you guys familiar with the quadratic equation, aren't we? And now in chapter 15, we just said, oh, we're just going to stick with easier ones. We'll get to the quadratic ones in chapter 16. Yeah, so now we get to do some fun math calculations. That's right. So we have an X squared over a 0.25. You know that 0.250 minus X is what we call like a polynomial. You don't separate that. You got to keep that all together. It's in the parentheses. Okay, we keep that all together. You can't separate that just yet. Oh boy, that's going to make it difficult for us. Well, to make our lives a tad bit easier, we're going to go with what we call an assumption. Now, if the assumption of we're going to assume that if my percent ionization is less than 5%, then what we're going to assume is this 0.250 minus X. So if the percent ionization is very small, that means this X is teeny tiny, right? Small percent ionization means small X value. So 0.250 minus a very, very small number ends up being 0.250. So that's what we're going to assume. We're going to assume that the X is negligible only if percent ionization is less than 5. So we would have to double check our percent ionization. Well, now that's interesting because percent ionization means I need the hydrogen ion at equilibrium. So what we're going to do is go ahead and make the assumption so that I can get the hydrogen ion at equilibrium and then double check if it's true. If it's true, we're good. If it's not true, yeah, you get to rework it. Yay, with the quadratic equation. Woo!
Can we eliminate, because if we have quadratic, it's going to be 2 values of X. Can we eliminate the minus 1?
Right. So let's do it with the assumption first, and then we'll check to see if it works, okay? And then we'll talk about what to do if it doesn't. So here's my setup. Now we said we're going to go ahead and assume it's less than 5%. So that means this number really becomes 0.250, doesn't it? Okay, so let's put that in here. For the 0.25 minus X, we're just going to put in 0.250. Okay, and if I get rid of the X down here now, does this make it a whole lot easier to solve? Yeah, it sure does. Multiply those together, take the square root, and what does X equal if that's the case? 0.0106. Yeah, that's X.
I did the quadratic and I got 0.0108.
Ooh, yeah. So you're already working that quadratic. Oh, awesome. All right. Oh, but wait, we have to check our assumption. see if this is true. I mean, maybe we need that quadratic after all. So let's go ahead and check our assumption. So I need the equilibrium concentration of the hydrogen ion. Well, that's X, right? And we figured that out to be 0.0106 divided by my initial acid concentration, which in this case was 0.250 times 100. So percent ionization comes out to be what? What's 4.2%. Okay, so that's below 5%. So we're good, but it's getting close to 5%. The closer we are to 5%, the more variance we're going to get. If it's really low, then it's going to be almost the same. But, you know, we're at the upper edges of our 5%. But it's fine. So we can still make that assumption. Okay, so do you see how we made that assumption? Simplify our lives, and then we double checked. We're under 5%, so we're good. But what if it wasn't under 5%? That's what if it's over 5%? Just skip it. Okay, if it's 5% or greater, then it's going to be more complicated. So we're going to have to arrange this equation into the ax squared plus bx plus c and then use the quadratic. Okay, so if we're not familiar with that quadratic formula, that's in Appendix 3. Okay, so you can go ahead and review that in Appendix 3. But I thought, oh, let's just see what happens. So what I did is instead of writing it out on the board, I typed it in to the PowerPoint so we could all see it clearly. What would happen to that equation if we had to use the quadratic? So if we're a little hazy on our algebra, here it is. So we can take a picture of it or we can write it down. Yeah. So wait, there's more slides about this. So okay, so the first one, that's my Ka is equal to the 2.5 minus x. Everybody see that? Okay, so I have to simplify that. So I'm going to take the 0.25x and multiply it by the 4.5 times 10 to the minus 4. Okay, is equal to x squared. Now, when you're multiplying by this in polynomial in parentheses, we do have to be careful. This is like the distributive property. You guys familiar with that in algebra? So what we're saying is that when you multiply this number by the things in the parentheses, you have to go all the way through. So we multiply this number by the 0.250, keep the minus sign there, and then multiply by x equals x squared. Are we okay so far? Now then, when you multiply these numbers together, you get 1.125 times 10 to the minus 4 minus this to the x is equals x squared. Now remember, you have to arrange it in this format. Oops, that's supposed to be, typo, ax squared. Sorry about that. It's supposed to be ax squared right there. Ax squared plus bx plus c equals 0. So ax squared. So I need to arrange it in that format. So I do that because what I want to see is what the a, b, c values are going to be. Okay, so there should be an x right there. Okay, so ax squared plus bx plus c. All right, so a becomes what? 1. Okay, so a is 1. Does everybody see a is 1? Okay, so then b becomes this whole number, right? And c, notice it's a positive c, so c has to take that sign with it. Okay, so that's what your a, b, and c values are. Okay, so you just arrange it into this format so that I can find out what a, b, and c are, and once you know what a, b, and c are, then you plug that into the quadratic equation. All right, so we okay with this so far? Yeah. All right, let's go to the next page. There's the quadratic equation, and I need to put in my value for b, and that is a plus or minus, that's two signs there, and the square root, and then b squared minus 4 times a, and there's my c, it is a negative number. So this is my equation. Now I want to simplify that. So if you take care of what's underneath the square root sign, this is the number that you get. 2 times 1 is 2. Then I take the square root of that number, and this is what I get. Okay, now still plus or minus. At this point, I would separate that into two of them, one with the plus and one with the minus. So I'd separate it into two equations. Because whenever you do the quadratic equation, you're going to get two answers. So, everybody following that okay? All right, so far so good? Okay, then that's when I would separate it into two equations. One with the plus and one with the minus. Okay? All right, so when I do that, x is equal to 0.0104 and it's equal to a minus 0.012. You always get two answers. One of them is going to be a true answer and one of them is going to not be a true answer. We're like, well, how am I going to tell the difference? That's right. If it's a negative number, can I have a negative concentration? No, we can't have a negative concentration. So the negative number we can't take. So whichever one's a negative one, we cross that one out. So we would take only the positive one. So we won't be taking that one. Now, the number that I have left, 0.0104, is using the quadratic equation. Now, we got 0.0106, so it's pretty close, isn't it? Yeah, and we are at the upper edges of our 5%, close to our 5%. So you can still see it's still pretty close. So our assumption does hold true then, doesn't it? All right, does that make it more clear how we can use the quadratic equation?
I have a question. For our homework, if we get to do it, do we have to use this first and if it's not working, we can use that one right away?
You can. If you would prefer to use the quadratic equation every single time, then go right ahead. Some of us actually would prefer to do that. Maybe we don't want to mess around with that 5%. That's totally fine. If you want to do quadratic equation every time, totally fine. Just be careful because, you know, you can introduce some error in that calculation. But that's totally fine. And be careful what calculator you're using when you go into the testing center. Remember, nothing more than a TI-83. Yeah, you can't take an advanced calculator in there. All right. So far, so good? Yeah? So can we do that? So some of us might want to just do that every time. Other of us may just want to take the assumption. That's fine, too. So what do we think? Use your All right. Yeah. You think so? Yeah.
Well, yeah, what if it ends up over, then you're just going to have to recalculate all over.
All right, any questions about, this is the same ICE table we've been doing, isn't it? It's just our calculations are a little bit more involved because now we have a more complicated thing to solve with the quadratic equation if need be, or using an assumption. Okay, so we found x, but that's x, great, but is that the final solution? What were we looking for in that problem? We were looking for pH, weren't we? So we're not quite done then, are we? So we can't just say, hey, the answer is 0.0106 and I'm done. And I can't do that because I know this was a lot to get here, but you're not done yet. You still have to go another step, and another step is the pH. So if you take the pH of this number, then what would we get for our pH? pH is what? 1.997 or yeah. Okay, so this is the pH. So that would be your final answer. Okay? So let's not forget that part.
Yeah,
I know, we just got to the H and we're like, oh, all that work with it. Am I done? Yeah, the quadratic equation is like, oh, okay. Yeah, but don't forget, we're not quite done. You have to take the pH because we're adding that little part about the pH in here with these KAs. All right, so we can do KAs? Easy, right? Whew, so good, so good. All right. Well, if you can do that for weak acids, guess what? Weak bases too! Yay, weak bases too! Okay, so let's talk about what it would be with weak bases. All right, so let's put our acid-base equations up here so we can remember the definition of a weak acid or a weak base, what they do with Bronsted-Lowry. So we said HA for acid. We can add water. Do we have to add water with an acid? No, but we can go ahead and do that if we want. Or not. You know, we don't have to add water or not. Okay, but the definition of an acid was, what does an acid do? Bronsted-Lowry definition? Donates a proton. So everybody knows how to write that equation for donating the proton. Okay, so now let's talk about a base. What's the base definition? Bronsted-Lowry base definition? Ooh, accepts a proton. Now this is, remember, it's just a base all by itself in our aqueous solution, because base has to accept a proton from something. So we're going to accept it, in these cases, from water. So B minus plus water. Dynamic equilibrium, what's that going to produce? Base, this is base, B minus, B base, is going to accept a proton. So it's going to be HB, and it'll be neutral, yeah, because it was B minus and picked up H plus. So it's HB plus what's left? OH minus. Now, when we were doing the acid, we did not have to add water. We could, but we didn't have to. We could have written it just HA, acid donates a proton and leaves the anion. I could have written it like that. But how about a base? Not for base. Why not for base?
The hydroxide.
Yeah, we got to have somebody to donate, and the water molecule actually is a reactant now, isn't it? Whereas with the acid, it wasn't a reactant. Here it is. It's got to accept a proton from somebody. So it's going to be water in this case. So we would write that as HB plus what? OH minus. Okay, so this is a Bronsted-Lowry definition where we accept a proton, the base does. And also, it's the Arrhenius definition, isn't it? Because didn't we say what happens when you put a base in water? What does it produce? Yeah, do you remember the Arrhenius definition? Hydroxide? So yeah, so that's talking about a couple definitions there. But it's a base. It's very clearly a base, isn't it? You got that hydroxide ion going on. Well, let's write the expression. This is dynamic equilibrium. So K is equal to, what would be my expression? Okay, HB concentration times OH divided by, be careful, this is pure water. Just the B, not pure water. Remember, pure water doesn't appear in the equilibrium expression. So we don't put the water there. So this is my expression. Oh, and what are we going to call it? KB. Yep, KB, you got it. Hooray. KB. That's right. And B stands for base. You got it. Okay, so if I have this equation, I'm solving for KB. I'm not solving for Ka, right? Everybody clearly see that B stands for base, and this is not an acid, right? Okay, so this is a Kb equation. It won't be Ka. This is not going to be Ka. Now, when we were talking about Ka, we said the bigger the Ka, what happened to the acid strength? Yeah, stronger. So what do you think? The bigger the Kb, what? The stronger the base. Exactly. Oh, so got this. Okay, so here's a bunch of bases and Kb's. Remember we said the bigger the Kb, the stronger the base. And you guys all know how to write the equation. There's several examples of how to write the equation. Bases are going to do what? They're going to, what? Take a proton, right? Okay, so we would write these accepting a proton from water and leaving behind the hydroxide. Now, do you remember we talked about weak bases, a particular kind of weak base that has nitrogen in it? Ooh, what would we call those? Yeah, they all acted like ammonia. It was the amines, we called them, didn't we? Do you recognize these nitrogen compounds? Yeah, so these are going to be amines, right? Remember that? Okay, so pyridine, hydroxylamine, yeah, these are amines, methylamine. Okay, it accepts a proton. Look how we wrote that. We like to put the hydrogen next to the nitrogen because isn't that where the lone pair is? And the hydrogen proton comes along and right there by that nitrogen, so we want to put that right by the nitrogen. And it was neutral, and so when you accept a proton, what happens to the sign? It's positive, right? So if a nitrogen is positive, it's already accepted the proton, so we can't take another one for that nitrogen. Okay, so you see how we wrote those? Look at that one, C6H5N. So guess where you put the hydrogen next to the nitrogen? Yep, and don't forget there's a plus sign. Do you put the hydrogen here with the H5? No, it's not that. You can't do that because you can't change the structure of the C5H5. That's this. The hydrogen goes right there next to the lone pair. All right, so remember the amines? Okay, so watch that. When you see those are going to be basic, and they're going to be amine compounds. And we can write our Kb expression just like we did for Ka. Yay! Isn't that fun? And then we can do the whole thing all over again, this time with Kb. Whoa, yes, yes. Woo-woo, more ice table reviews. Awesome. Okay, well, we will work on that after the break. How about that? Okay, whew, time to get started back again. So, another ice table. Let's do another ice table. Okay, you guys know how to do this one, right? This is KB. Okay, codeine. Would you guys recognize that as a base?
Yes.
Codeine, would we? You're like, how would I know? Okay, it's got a nitrogen in there, right? Yeah. Does it have a hydrogen in the front that we could lose?
No.
No. So that would be a key thing right there. That's not an acid. Okay, so we would recognize that as an amine. Another clue would be the ene, codeine. Yeah. Okay, so could you recognize then that now as a base? Would you recognize it as a base? All right, and you know what bases do, right? What do bases do? Definition? Receive a proton. So you're going to write the equation, aren't we? Yeah, got to put it with water. Write the equation. Okay, so write the equation. You guys know the definition of a base, so we were just talking about how we can recognize that as a base and not an acid. Okay, so let's set up the ice table. And let's see what happens. So we would have C18H21. This is our codeine. Okay, you're going to have to add water, right? Yeah? Got to add water? Okay, so let's write our structure back down here. H21, NO3, and then we're going to put an H at the end, plus, that's kind of close to the nitrogen, plus OH minus. Everybody can do that. All right, then we set up our ice table, ICE. Okay, we know that. Put in your concentrations that we get from the problem. So, a 5.0 times 10 to the minus 3. Okay, that's my initial concentration, 0.0050 molar. Great, I got that. And has a pH. pH. Okay, does anybody notice we don't have any hydrogen ions? Now what is it? What am I supposed to do with pH then? Find the pOH. Exactly. Have we not done that? Okay, find the pOH. Okay, I find the pOH. Now what? I subtracted that from 14 and I got the pOH. Concentration of the OH, hydroxide ion then, isn't it? Okay, does everybody see how I would get the concentration of the hydroxide ion here? Yeah. Okay. So are we good with that? So you'd say 14 minus the pH, that gives me the pOH, and then find the hydroxide ion concentration. So what are we getting for that hydroxide ion concentration then?
8.91.
Okay, 8.91 exactly, times what? 10 to the negative 5. Perfect. All right, and then we know how to finish the rest of that ice table, don't we? Yeah, so we got to get the rest of these. So let's go ahead and put in our zeros and then find our change. So it's 1 to 1, so that makes these changes easy. 0.91 times 10 to the minus 5. This is a minus 8.91 times 10 to the minus 5. And we know how to find all those. This becomes like very close to 0.005, right? 0.00491. This is 8.91 times 10 to the minus 5. There we go. So is this a Ka, by the way, or is this a Kb? Kb. It is Kb. Now, do I have to worry about water? Gosh, we don't have anything for water. No, because, yeah, it's a pure liquid. Of course not. Exactly. So we don't put that in there. So those are our concentrations. So let's put that into our Kb expression. And our answer, if we put that into our Kb expression, comes out to be Kb is equal to those concentrations. So what does it come out to be? 1.6 times 10 to the minus 6, right? Did you guys get that for the Kb? Did you plug all those values in? The 8.91 times 10 to the minus 5 times 8.91 times 10 to the minus 5 divided by the 0.00491. And is that what we get? 1.6 times 10 to the minus 6?
Yes.
Okay, there we go. Same thing, except we have a little bit going on with the pH, and we use the pH to find the OH concentration. That's the one little thing we're adding on to our ice table. Okay, so we're going to use the pH to find that OH concentration. All right, so you know what? We can go again, can't we? Ooh, boy, let's do more. This time we're going to find pH. Okay, so we want to find the pH, don't we? This is a dimethylamine. Again, do you recognize this as a base?
Yes.
It's not an acid, is it?
Yes.
Okay, so you know what happens to bases. All right, so go ahead, set up your ice table. Write that equation of a base accepting a proton from water, and then solving that. Oh, but it says wasn't our ice table supposed to be in what? What units do we usually like our ice table to be in? Molarity, concentration is molarity, or atmospheres, but in this case, concentration and molarity. Do I have molarity? No. Oh, how am I going to get molarity? Yeah, moles over liters. So that means I need to change the grams to moles, and the milliliters to liters, and then divide that out to find the molarity, right? And then we could do our ice table. And then we can find the pH. All right, see if we can work on that one. Yeah, you make the assumption on this one. So we found the initial molarity is 1.5, and then put those equilibrium concentrations into your Kb. So if you make the assumption, it's easy to solve, isn't it? Yes. So if we make the assumption, what are you guys getting for x? X is equal to 0.028 what, 446, 0.02846? Okay, so if we plug that back in to get the percent ionization, what's the percent ionization come out to be? Did anybody do that one? That'd be what? 0.02846 divided by 1.5 times 100. 1.9%. Okay, so our assumption works then. So we can use the assumption for this one. All right. So if the assumption works, I found X. Is that my final answer? No. I need pH. Is this a hydrogen ion concentration? No, it's hydroxide. So it's the OH. So how do we get pH from OH? How do we do that?
1 into 10 to the power negative 14 divided by that.
Or we could say POH, right? Minus log OH. We get the POH and subtract that from 14. So if you get the POH, that's great, but you do have to remember to subtract that from 14. And if you forget that, your pH will be off. But if you think about it, this is basic. So if you forgot to subtract it from 14, you're not going to get a basic pH, are you? So that should be the clue to you that you've forgotten something, if you get a pH that's acidic when you're working with a basic solution like this. All right, so we take the POH, subtract that from 14. What are you guys getting for the pH? Did everybody get pH is 12.45? Yep, that's it. Do you have any questions? How are we doing? Okay. All right, so this was the hydroxide ion concentration, remember. And then from the hydroxide ion concentration, we need to find the pH. So we ended up with a pH of 12.45, which is basic, which would make sense, right? Okay. Questions about that one? No? We're just cranking right through. So easy. You guys are just like, oh, so getting it. Okay. So we've done those ice tables over and over again, haven't we? We did it with an acid. We did the whole thing all over again with a base.
So basically, all of test 3 is ice table. Is that
Oh,
what
yeah.
you're saying?
Oh, yeah, yeah. Except for the strong acids and strong bases, which would not use an ice table. So then, the question is can you remember which was an ice table and which one doesn't? Because remember, we did the strong acids and strong bases without an ice table. But weak acids and weak bases do need an ice table. So now you really need to distinguish between those. Now, when we did the weak acid, that's going to be region 1 of a weak acid-base titration. And when we were doing strong acids, strong bases, strong acids was region 1, strong bases is region 4. So we're working on the regions now. Okay, so now that we understand Ka and Kb, let's think a little bit more about that. Okay, if I have a strong acid, a stronger weak acid, okay, so if I have a stronger acid, what happens to the Ka then? Goes up. So if I have a stronger acid, what can you tell me about its conjugate base? It's weaker. So if a base conjugate base goes weaker, what happens to the Kb? Goes down. So then how are Ka and Kb related? They're inversely related. It's not just any Ka and Kb, it's only inversely related if it's a conjugate acid-base pair. Okay, has everybody got that? A conjugate acid-base pair. The Ka and Kb are related. Because we know the stronger the acid, the weaker the conjugate base. Right? Okay. And the weaker the acid, the stronger the conjugate base, right? So the Ka and the Kb are going to be inversely related. So no matter what we're doing, when you multiply them together, we're going to get a constant. And what constant would that be, pray tell? It's going to be Kw. Okay, so Ka times Kb is Kw. This is another one of those little equations that we're going to need to remember. It's Ka times Kb is Kw. We need to remember that. Okay, because all sprinkled through the test, there's going to be situations where you're working with a base, but you're not going to be given Kb. You're going to be given Ka. Are we going to remember that? Like, oh, are we going to notice that's a little a, and we're working with a base? So then we're going to have to use this equation to find the Kb. Because whenever you're working with a base, you have to have the Kb. Whenever you're working with an acid, you have to have the Ka. So you're going to have to pay very careful attention in the problem. Do you have the Ka when you need the acid? And do you have the Kb when you need the base? And if not, can you convert one to the other? Yeah, because you remember that constant Kw, right? Okay, so if you have one, for example, Ka, now remember this is a conjugate acid-base pair that we're talking about how this is related together. So if I have Ka for the conjugate acid of a base, Kb, what is the Ka for that? Well, you guys do that, right? That would be Kw divided by our Kb, and that gives us the Ka. So the Ka for this answer would be what? What you guys get? Can you divide that out? Kw divided by Kb, and what do we get for Ka? So Ka times Kb is equal to Kw. So Ka times Kb is equal to Kw.
1.78.
1.79
So would everybody get 1.8 times 10 to the minus 4? Okay, because Kw is 1.0 times 10 to the minus 14. So we divide that out and we get 1.8 times 10 to the minus 4? Okay, awesome. So we need to remember about the Kas and the Kbs because you have to make sure A is for acid, B is for base. Okay, great. Well, we're talking about acids and bases. And you know acids and bases can react together, don't they? And a general rule of thumb, particularly with the aqueous solutions that we're talking about here, is acid plus base produces salt and water. That's right. So when you have a salt, we don't have any more of the original acid, or we don't have any more of the original base, do we? Because they've neutralized each other. So acid plus base is salt and water. Well, we've taken the pH of an acid. We've taken the pH of a base. Can we take the pH of a salt solution? Yeah. Hey, so now that we know about acids and bases, and we know acids and bases react together, so let's take the pH of a salt solution. Let's do that. Let's talk about acids and bases reacting together. So acid plus base gives us a salt and water. So let's think of an example. Let's say acid, hydrochloric acid. Hey, is that a strong acid?
Yes.
Yes, okay. Plus, let's pick up a base, aluminum hydroxide. Hey, is that a strong base?
No.
No. Okay, produces our salt and water. What's the salt? Al chloride 3, right? Because you remember the charges, don't we? And we know how to write that correct ionic compound based on the charges of the aluminum ion and the chloride ion. Yep, we got to remember that when we're talking about these ionic compounds. Okay, so for hazy, you might want to review that. So this is how we would write the correct ionic compound, plus H2O. Okay, now is it balanced? No. What do I need to do to balance it?
3HCl and
Okay, 3HCl and what else? 3H2O. Anything else? Are we balanced now? Yeah, we are balanced. Okay. All right, so when we're writing acid plus base gives us salt and water, you might want to refresh your memory on how to write that ionic compound based on the charges. That gives us the correct subscripts and make sure it's balanced. Okay? All right, so let's take a look at that salt. Because when we have this salt, we don't have any more of hydrochloric acid or any more aluminum hydroxide. We have the salt. So let's take the salt. You guys recognize an ionic compound? How can you tell if you have an ionic compound? Metal and nonmetal, or cation and anion, usually metal and nonmetal. All right, so let's take a look at that cation. And let's take a look at the anion. Okay, so the aluminum ion is my cation. Where did that aluminum ion come from? Where did aluminum come from? From the base. Okay, so cations come from base then, don't we? Have that. Cations come from, okay, so we can see cations are coming from the base. Cations are coming from the base, and where are the anions coming from? From the acid. So let's take a look to see what happens with the anion and cation in water. How does that affect the acidity? So let's go back to what we were talking about with our cations and anions. So let's go back to cations. You remember how we said, oh, if you dissolve the cation in water, some cations, which are large and have a low charge, you know, they draw the electron density toward them, but not strong enough to where the hydrogen ion would easily leave. But here, when you have a smaller, higher charge, what happens? You know, right? Okay, they're like, whoop! Okay, so then what happens to the hydrogen ion? The hydrogen ion, like, it runs away. Now, if the hydrogen ion leaves, what does that make my solution become? More acidic. Yes. So some cations do make the solution acidic. Some do not. Question is how do we know which one is which? Because we have to know which one is which. Well, we can know by, interestingly enough, the ones that do this, that do not affect the acidity, are going to be our strong bases. Oh, okay, so now we can have a general rule that says cations from a strong base. Okay, so let's put that up here. Cations from a strong base, no effect, right? Nothing happens, no effect. And what are those cations from a strong base? Do we remember those from the strong base? What are they? Okay, group 1A, calcium, strontium, and barium. So anytime you have any of those cations, is it going to affect the acidity? No, right. And it's not going to affect the acidity, right? Because it's going to be like this one. Does that make sense? So anytime we have any of those cations, then what do we expect it to affect the acidity? No. Okay, nothing. So it'll be nothing. All right, so cations, so the other cations, and they're coming from a weak base, would make the solution what? More acidic. Okay, so all the other cations are going to make it acidic. These cations, group 1A, calcium, strontium, barium, won't. Okay? All right, are we okay with that? Does that make sense? All right, so if I have these ions up here, so let's put sodium ion, let's list calcium ion, let's list the iron 3+ ion, potassium ion, ooh, and let's do ammonium ion. Let's throw something interesting in there. Okay, let's decide if it's going to be acidic or no effect. Okay, are we ready? Decide? All right, so let's talk about sodium ion. No effect. That's right, very good, no effect. How about calcium ion? No effect, very good. Iron ion? Acidic, perfect. Potassium? No effect, right? Because isn't it in group 1A, right? No effect, yeah. Okay, and how about the ammonium? Ooh, it's acidic. It is acidic because isn't NH3 a weak base? Yeah, it's not one of those strong ones, right? So this would make it acidic, even though it looks a little different, NH4+. Okay? All right, whew, got the cations. Oh, so straightforward, simple. Okay, now let's talk about the anions. Okay, so let's do anions. All right, we said the anions come from the acids, right? Okay, so the chloride ion is a conjugate base of hydrochloric acid, isn't it? Okay, so let's write that pair. Hydrochloric acid, chloride ion. That's a conjugate acid-base pair. Hydrochloric acid, what kind of acid is that? Super, super strong, right? So what kind of conjugate base is that going to be? So weak it's like negligible. Remember? The stronger the acid, the weaker the conjugate base. Okay, so this is super strong acid, so that's like negligible base. So negligible base isn't going to do anything, is it? So if I tried to say chloride ion plus water, what do we decide is going to happen? Nothing. Okay. So then we could say if an anion then, so an anion from what? A strong acid, no effect, right? Now what are those anions? Oh, what anions were from the strong acids? Yeah, there were 7 of them, weren't there? And what were they? Okay, so HCl, so I'll put chloride ion. What else? Okay, bromide ion, because we have hydrobromic acid. Iodide ion, because it's hydriodic. Nitrate ion, that's right, because nitric acid. Okay, sulfate ion, because it's sulfuric acid. Perchloric ClO4 minus, right? And one more. One more. ClO3 minus. There you go. Okay, so chloride ion, bromide ion, iodide, nitrate, sulfate, perchlorate, and chlorate, right? Those are the ions. Any of these ions come from, where did any of these ions come from? Strong acid. So that makes these all be negligible bases. Okay, great. Well, let's think of an acid that's not strong. How about acetic acid? C2H, C2, 3A, acetic acid, right? Okay, so let's write its conjugate base. C2H3O2 minus. So if this is a weak acid, it is a weak acid, right? What does that make this be for the conjugate base? Strong conjugate base. All right, so the strong conjugate base is going to do something. Let's write that down. C2H3O2 minus plus water. And what does a strong base do? What's the definition of a base? What do? They gain what? A proton. Right? Isn't that what a base would do? If this is a fairly strong base, it's going to do what? Accept a proton. And accept a proton from water. Hey, didn't we write those before? Yeah, so what reaction are we going to get? We're going to get, that's right, plus OH minus. So I'm going to get my acetic acid plus the hydroxide ion. So guess what this is going to make the solution? This hydroxide ion over here is going to make the solution be what? Basic. So then we can say, oh yeah, anions from weak acids are going to make my solution more basic. And there you go. All right, so those are our 4 options, 4 possibilities. Okay, so we'd be able to pick out which anions have no effect and which anions are going to make the solution basic, right? Okay, questions about that? Okay. Well, these are our 4 choices. Cations from a strong base, cations from a weak base, anions from a strong acid, anions from a weak acid. Those are our 4 choices. And we know what's going to happen. So we can make a combination from any of, we can have 4 different possible combinations in our salts based on cations and anions. So let's take a look at what happens. Cation from a strong base. If the cation is from a strong base, what did we say? No effect. Okay, negligible. Anion from a strong acid. What did we say? No effect. So if I've got no effect and no effect, guess what? Neutral. No effect. Right? So any salt made up of these 2 anions, cation and anion, these 2 right here, these 2 ions, is going to be a neutral salt. It's not going to affect the pH at all. Make sense? All right, let's go to another one. Strong base. What do we say happens to strong base? No effect. And what do we say happens with a weak acid? Weak acid, anion from a weak acid makes it basic. Okay, so this, no effect. Here, basic. So you put those together and what do we get? Basic. Okay, let's go again. Weak base. What did we say was a weak base? Acidic. And then strong acid. Nothing. So now I have acidic and nothing. Ends up being acidic then, doesn't it? Okay, and the very last one. Weak base. What would that be? Acidic. Weak acid. Basic. Uh-oh. Oh. It depends. It depends on which one is stronger. Which one is stronger?
We have
Okay.
to calculate the pH for both of them and compare.
Ooh, well, you know what? We're not going to calculate the pH. Instead, we're going to talk about Ka and Kb, because doesn't that help us decide if it's stronger or not? Because we want to know which one is stronger. So we'll use the Ka and the Kb. So let's see what would happen with the Ka and the Kb. Okay, so let's take an example of something like that with Ka and Kb. All right, if the Ka is bigger, then we're going to have something being what? Ka is bigger, more acidic. Okay, so if Kb is bigger, then we're going to have something more basic. Okay, so let's take a look at NH4 and F. Okay, NH4, ammonium fluoride. So let's see, ammonium. Okay, so we're looking at the cation here. So that we can tell is not one of our strong ones. So it's going to make the solution acidic. Okay, so the ammonium is going to make the solution acidic. And how is it going to make the solution acidic? What do acids do? Donate a proton. Okay, so let's write that, donating a proton, shall we? There's the proton plus what's left behind? NH3. Okay, so this is a proton, so that's going to be a Ka, isn't it? All right, so the Ka for this is 5.68 times 10 to the minus 10. That's the Ka. Okay, now let's take a look at the fluoride ion. Fluoride ion, okay, anion. Is it one of these anions that have no effect? No, so that anion's going to be basic. So you know what an anion will do. We add that to water and we would get HF plus OH minus, which we've seen already, and that's a Kb, and that Kb is 2.9 times 10 to the minus 11. Okay, which is greater, the Ka or the Kb? Ka. Does everybody see the Ka is greater? Okay, Ka is definitely greater. So it's going to end up being what? More acidic. Ka. Ka is stronger, yeah? Yeah, so that means we got more of these hydrogen ions, right? Yeah, a lot of times more. That's right. So isn't it going to be more acidic then? Okay, so do you see how we did that? Okay, so let's just practice a couple of these. Let's look at strontium. All right, so let's look at the cation, strontium. Hey, is it one of these listed from a strong base? Yes. So no effect, right? Okay, now let's look at chloride ion. Is that one of our no effect ions? No. Yeah, okay, so what do we got? No effect, and no effect is neutral. Okay, let's look at another one. Ooh, that cation. Let's take a look at our cations. Is it one of the group 1A or calcium, strontium, barium cation? No. So therefore, it's going to be acidic. It's an acidic cation. Well, now let's look at the nitrate ion. Oh, that's one of our listed no effect, isn't it? So that's going to be acidic. Okay. And then same thing here, sodium. Let's look at our sodium. Oh, isn't that in one of the group 1A that we've listed? Okay, so the sodium's going to have no effect. What about the acetate anion? Is it one of our listed? Nope, so that acetate ion is going to be basic. So what have I got? Basic solution. And then here's the one that we were just talking about. Okay? All right, does that make sense on how you can talk about what the pH is generally of a salt then? Okay, so what we're going to do now is we're going to go through and decide which one of these are acidic and which one of these are basic or which one of these are neutral. Okay, so see if we can work on that. Now what we're doing is we're just getting a general idea of what's acidic, basic, or neutral. Then we actually get to calculate what that pH is. Yeah, that'll be the fun part. All right, so decide which one of these is acidic, basic, or neutral based on our rules. Okay, so are we checking? Did you guys check with your neighbor to make sure yours is right? And you wrote them all down? So are we ready to check our answers? What do you think? Yeah? Okay, let's see what we got here. All right, so as we go down the list, just tell the class what it is that you decided about yours. Okay, so we'll start with the first one, sodium chloride. What did you decide? Okay, she said neutral. Okay, and the next one? Okay, acidic. Okay, KBr. Okay, neutral. And then potassium nitrite. Okay, he said it was basic. Okay, the next one, ammonium chloride. Okay, she said acidic. Ooh, here comes a fun one. You got a fun one. What? Basic. And why did you choose basic? That's right. Does everybody see KB is bigger than KA? KB is bigger than KA, right? Watch those exponents. Yeah. All right, so the KB is bigger than the KA. Okay, so that's why it's basic, right? Okay, how about who's got strontium chloride? Okay, neutral, very good. Calcium fluoride? Basic. Good, basic. Okay, iron 3 chloride? Perfect, acidic. And the last one? Basic. Whoo, boy, you guys nailed that. Oh gosh, you guys are doing so good on this acid and base stuff. We are really knocking it out. That is so awesome. You guys are getting the pHs and the OH, and we got the Ka and the Kb, and now we're even talking about salts. How about that? All right, well, let's see. We did take the pH of a Ka. We did take the pH with the, Ka stuff, and take base and pH and Kb. Oh, but now we have these acid solutions. So what we were just talking about just now is deciding, ooh, is it going to be acidic, or is it going to be basic, or is it going to be neutral? The next thing that we want to talk about is how to find the pH of a salt solution. Okay, so now that we've got a general idea of what it is, then what is exactly the pH? Now, when we determine the pH of the salt solution, you got to remember how to do this, okay? Because if you come up with a pH of a salt solution and you know it's an acidic salt and your pH is coming up something different, it's coming up basic, you got a problem, right? So you can use this as a general guide to check you as we start to learn how to calculate the pH of salt solutions. So are we going to remember these 4 rules? You guys are going to remember these, right? Are these going to be given to us? No. Okay, but you know what? Doesn't it kind of go along with our strong acids and strong bases? So you mean we still have to know which are the strong acids and which are the strong bases? Yeah, we sure do, don't we? All right. Okay, you guys done a good job. We'll pick up with what those pHs are on Thursday.